Hello everyone, my name is Alexander Kukushkin and I work as a principal software engineer at Microsoft. I'm a Postgres contributor and today I'm going to talk about synchronous replication in Postgres and some myths and truths about it. If you are application developer or DBA, this talk might bring very interesting insights about these topics. Okay, let's dive in. We should start with defining what write-ahead lock is, because it's a central point in Postgres which makes sure about your data integrity, and on top of it, Postgres implements recovery, archives, replication, and so on. If you look into Postgres data directory, you will find in the PGWall a whole bunch of files with hexadecimal names, which typically 16 megabytes in size. Although one may change size of write-ahead log file. On top of write-ahead log, Postgres implement replication. And there are two types of main types of Postgres replication. One is a log shipping replication, which is implemented on the primary by calling archive command. Archive command simply supposed to copy write-ahead log file to some remote storage. And on the standby node, there is a restore command, which copies write-ahead log file from remote location to PGWall directory, and Postgres will be able to replace this file. Besides that, on top of write-ahead log, Postgres implement streaming replication. And there are two types of streaming replication. One of them is a physical streaming replication, which is the main topic of this presentation. And the second one is a logical replication. Let's look at how physical streaming replication works. On the primary, Postgres write WAL files to PGWall directory, and there is a special process on the primary that exists, and name of this process is WAL sender. In fact, this process does not exist on its own. It is being started when WAL receiver on the standby node connects to a primary and starts asking for write-ahead log files. WAL sender streams content of write-ahead log files to WAL receiver on standby node, and WAL receiver on standby writes those files to PGWall directory. Surprise! It will be in this totally the same format, and content of those files will be exactly the same as on the primary. Besides that, on the standby node, there is a special process type which is called startup process exists. It reads files from PGWall directory and applies changes, transaction changes to the database. Basically, this way we get standby, which will be fully identical to the primary. There are two types of physical streaming replication. One of them is asynchronous. It means that when you execute transaction on the primary, it simply writes it to write-ahead log, flashes it to disk, and it is being streamed to standby. And your application doesn't wait until a transaction received by synchronous standby or any kind of standby. And the second type of streaming replication is asynchronous replication, which is the main topic of this presentation. And in synchronous replication, primary has to wait until a synchronous standby, one or many, depending on the configuration, confirms that they received, saved to disk, flashed, or replied your transaction. Before it happens, your application will not get a notification that transaction was successfully executed. And there are two types of configuration parameters that control synchronous replication. One of them has name synchronous commit, and the second one synchronous standby names. Let's dive deeper into every of those configuration parameters. The first one is synchronous commit. By default, Postgres sets synchronous commit to on. It guarantees that transaction that your application executes is durable locally on the primary. It also guarantees that it will be replicated to a standby, and it will be durable in case if Postgres crashes or the entire operating system or the entire server crashes. In case if you want to get confirmation only when transaction is already applied by standby and visible on the standby for client queries, you should set synchronous commit to remote apply. This setting must be set on the primary node. That's important. In case if you don't care about durability on server crashes, you can set it to remote write. And of course, like in this case, it will not be waiting for remote apply. And the second parameter is called synchronous standby names, and it defines two types of synchronous replication. The first type is priority replication. To use priority replication, you need to use very special format of synchronous standby names. You say first a number and then list of nodes that you want to have synchronous in parentheses. The way it works is that primary will be waiting from first nodes in the list for confirmation that transaction was either received, flushed to disk, or applied on the standby node. If the first node from the list does not respond, for example, it crashed primary, will switch to the second node and will wait for confirmation from a second node. It has certain disadvantages because it may take some amount of time for primary to realize that node 1 in the list is not responding correctly before it will switch to node 2. That's why in Postgres 10 we got a quorum type of synchronous replication, and to enable it, you should use slightly different syntax of synchronous standby names configuration. Instead of first, you say any, and again number of nodes that you want to have synchronous and the list of nodes. In this case, primary will be waiting for confirmation from any node. Whichever standby node is faster confirming, that sort of wins, but it does not ruin guarantees that your transaction was committed, safely committed to more than one node, which is a primary. And let's try to discuss some myths about synchronous replication and try to bust them. The first myth that I really like, and sometimes people don't understand how it works under the hood, is the people usually think the transaction is committed only after receiving confirmation from synchronous standby nodes. This is entirely not true, because the truth is transaction is always committed first locally. But primary holds locks, and transaction does not become visible until sufficient number of standby nodes confirmed that they received, flushed, or applied this transaction. And locks are released when number of necessary numbers of confirmations is received. However, there are exceptions. Transaction might become visible when a query is cancelled. Like, for example, your query or your commit query is cancelled, when connection is broken, or, for example, when Postgres is restarted and you reconnect, and you will see the transaction is visible, although it wasn't replicated to a standby node. Let's try to see on the picture how the entire workflow of synchronous commit works in case if we say a synchronous commit is set to remote apply. It means that standby must apply transaction before primary can confirm to the application. Application sends a commit request to the primary. Primary writes commit log record to PG wall directory. Wall sender reads this commit record from PG wall and sends it to wall receiver on the standby node. Wall receiver writes commit record to PG wall on the standby node. Startup process reads from PG wall and applies your transaction. After transaction is applied, standby sends confirmation via the same TCP channel between wall receiver and wall sender. the same connection that receives data, and it notifies primary that transaction was successfully applied. Only after that, primary will release logs and send confirmation to the application that the transaction was successfully committed. You see how many steps there are, and in fact, commit happened first locally, and only after that it was sent to a standby node. So I think the first myth was busted, and therefore we continue with the second myth. Many people think that synchronous replication guarantees a zero point in time point recovery objective. Or it means that they will not have a data loss in case if they fail over to a synchronous node. The truth is, it depends. First of all, application may disable synchronous commit per connection in case if they want to or if they need to, by setting synchronous commit to local. In this case, a transaction will be written only to a primary, and application will not, and primary will not wait for confirmation from standby nodes before sending success to the application. And the second point, transaction also becomes visible on the primary when lock is cancelled. It may happen when application actively cancels query, or DBA may also cancel this query when TCP connection between application and the primary is broken, when Postgres, for example, restarts. How can we emulate this behavior? We start a single node Postgres and we set synchronous standby names to unknown, which means that it is supposed to get confirmation from the node, from synchronous node with the name unknown. Since this node does not exist, our transaction on the primary will more or less wait forever. So we create a table from a select query, and it hangs. Therefore, we just press Ctrl+C and cancel our query. And when after that we run select, we notice that table test, which supposed to be not created or not become visible until it was replicated to the standby node, in fact, is there and it is visible, and we can read from this table the number of rows that we insert. For some people, it is a big surprise, but this is how it works in Postgres. And in fact, it's a very big problem, such cancelled waits, because it may lead to visible data loss if synchronous standby is promoted. There is some discussion happening on the Postgres hackers mailing list, and this discussion, this mailing thread exists for, I think, 5 years, maybe longer, and unfortunately, it's not moving forward. But as far as I know, most of the cloud providers or some big vendors implement their own patches to mitigate this problem. And I don't understand why in Postgres core such patches are still not present. But it's not the single problem that transaction becomes visible on the primary after it's being cancelled. In fact, let's think about a situation when TCP connection between application and between primary was interrupted. In this case, application will need to decide whether it needs to retry this transaction or maybe it should not, and it has to somehow figure out the state of this transaction after reconnecting. And there are a couple of approaches to mitigate this problem. The first one exists for many years, and it's called two-phase commit. It's not easy to use on the application side, and it requires you some to put a lot of effort to implement it correctly. The second approach, which you may use, it's a special function which is called TXID status. It allows you to check whether your transaction, or like not exactly your transaction, but some transaction with transaction ID was committed, aborted, whether it's still in progress, or maybe Postgres uh, uh, does not have current information about it already. How it can work? We start transaction on the primary, we insert some data in create table, insert some data into it, and before committing, we get transaction ID by calling function txid current. We can check in pgstat activity that, like, after hitting commit, Postgres is waiting for synchronous standby to confirm. And we will see in the pgstat activity wait event type and wait event, which are set to IPC and sync-rep respectively. If we kill our connection, and if and in my case, I also killed PSQL application. And after reconnecting, we can check status of our transaction by using txid status. And as you can see, transaction was successfully committed, although it wasn't replicated to a standby. And it's also visible, which is not nice. All right, so coming to the third myth, some people think that reading from synchronous standby nodes is like reading from the primary. You can, like, when you execute transaction on the primary, after that, like, you immediately can see it from the synchronous standby nodes. It's not entirely true, because transaction on synchronous standby is visible immediately, while primary may be still waiting for more synchronous standby to confirm. And it means that, like, if you run a query and get result on the standby, like fresh result on the standby, and you run the same query on the primary, you may not see such results because it is still waiting. As a result of that, please never do write on the primary based on reads from a standby. There are more side effects of this behavior. In fact, asynchronous standby node can be ahead of synchronous nodes. It means, like, when you're reading from asynchronous node, you may also see some features that never happened, in case of primary failed and synchronous nodes didn't manage to replicate some transactions. And it is a big surprise to many people, but logical replication connection exhibit exactly the same behavior by default. If you don't configure your Postgres 17, like, in a very special way, or if you don't use PG failover slot extensions to mitigate it, your your application that relies on logical replication, again, may see some events that didn't made it to synchronous standby. And there is no easy way to rewind your logical replication. And the last point on this slide, with quorum-based synchronous replication, you never know which standbys in fact are synchronous. You may randomly pick some of them, but it doesn't mean that they receive the latest transaction. In case if you want with 100% certainty read from a standby the same transaction in state, like you after executing it on the primary, you have a few options. First one, you need to set your setup to be fully synchronous by listing all standby nodes in synchronous standby names, and second, number of nodes equals to number of nodes you have. The second option, you need to implement some logic in your application, which will be waiting for synchronous standby to catch up with the primary. The way it works, like, before committing transaction or after committing transaction, you need to get current wall insert LSN, and you need to wait until standby replay up to this LSN. It would be nice to have a function in Postgres that implements such behavior, but it's not yet there, although discussion in the hackers mailing list are happening. Okay, and now the myth number 4. If we run synchronous replication, we don't need to use PG rewind. The truth is that wall on the primary is written independently from standby nodes, and while your application is waiting for a confirmation from the primary, some parts of walls of write-ahead log maybe didn't make to a standby. And as a result, when primary fails, there will be no visible data loss. But some, but primary managed to write a bit more write-ahead log than standby, than the point when standby promote. It also may happen not because of transactions, but because some background job in Postgres like vacuum or after vacuum are running. They are changing some data, they are writing logs, but they are not, I mean, like they are not changing your data, they are changing the data pages. But again, they are generating write-ahead log, and it may lead to the same problems. What means that PG rewind is required, like even in synchronous setups. And there is one more point when PG rewind might be required. For instance, there is asynchronous standby, which is a bit ahead of promoted synchronous node, which is totally fine because we made promise that transaction that there will be no visible data loss when we promote standby, asynchronous standby, but we don't count on asynchronous. And in such case, asynchronous standby also must be rewound. And the last myth in this presentation for today is that synchronous replication is slow. In fact, it's partially true, and to understand like what is happening under the hood, I did some benchmarking on my laptop. I put benchmarking in double quotes because my laptop is not powerful, of course. And to run benchmark, I used Docker Compose. I started 3 Docker containers with Postgres, and I used IP route 2 tool to emulate latency between Postgres nodes. I was using more or less default Postgres configuration, only max connection was a little bit increased in order to handle required number of connections from pgbench, which was initialized with scalar factor 100. And on my laptop, synchronous commit was set to on, again default, and I was testing 2 different setups: priority synchronous replication and quorum synchronous replication. And here are the benchmark results. Please don't take it as a reference. Like they just prove some like certain points about how synchronous replication affects your transaction latency. Not more than that. And as you can see, latency of a single transaction in asynchronous setup was 5 milliseconds. And with synchronous replication, with quorum replication, it's already 12 milliseconds, and with priority replication, synchronous replication, it is 14 milliseconds. And transaction rate is almost twice smaller in asynchronous versus synchronous. Although when we increase number of connections, the transaction rate of synchronous replication is increasing a little bit. When we increase latency further, like between nodes to 5 milliseconds, we see that correspondingly latency of our transaction is growing. But the total latency of transaction consists of more or less 3 numbers, like latency of disk on the primary, latency of disk drive on the standby, and round trip latency between nodes, which more or less matches this number. When we increase round trip between nodes even further to 10, from 5 to 10 milliseconds, we see that TPS latency is also increased by almost 5 milliseconds, maybe slightly above. And when we finally set round trip between nodes to 100 milliseconds, we see that transaction latency increased above 100 milliseconds. And at the same time, TPS really dropped for synchronous workload. What are outcomes of this benchmark? First of all, speed of synchronous setup depends on hardware and round-trip time between nodes. Please don't run synchronous nodes between continents because your application will be very slow. In most cases, for asynchronous setup, additional latency, transactional latency, is introduced by round trip between nodes. And it happens because clients has to wait until synchronous standby confirms when it received, flushed, or applied transaction. You can scale, of course, TPS by increasing number of connections, but final TPS will be always lower. So that was it for today in my presentation. Thank you for listening, and if I'm here to answer all your questions.